So we have this series sigma n equals 3 to infinity of 9 times 3/7 to the n power. So, well, we need to make sure that our series starts at n equals to 0, alright? So what we need to do is get rid of that 3 by subtracting a 3, alright? So minus 3, but if we subtract the 3 from the starting index, we need to do the opposite in every single instance of n in our series. In this case, that's a plus 3. So that'll make the series go to from n equals 0 to infinity, 9 times 3/7 to the n times 3/7 to the third power. And well, let's just simplify the numbers. In this case, 3 cubed and 7 cubed. 9 times, is that 27 over 343? And times 3/7 to the third power. And well, 27 times 9, is that 243, I think? So this is sigma n equals 0 to infinity 243 over 343 times 3/7 to the n power. So in this case, we have the series in the correct format. Number 1, the starting index being an n equals to 0, a times another value r, which is raised to the n power. So let's identify those values. A, which is 243 over 343, and r, which is 3/7. Well, in the case in which, okay, so for r equals to 3/7, let's take the absolute value of 3/7, which is 3/7, and this happens to be less than 1. For this reason, the series converges. And it's possible to find the infinite sum. So let's use the formula. S sub infinity equals a over 1 minus r, which is a 243 over 343 divided by 1 minus 3/7. Well, this is the same as saying 7/7 minus 3/7, which is 4/7. So this is 243 over 343 divided by 4/7. So let's rewrite this as 243, and I'm going to rewrite this 343 back as 7 cubed, just so you can see how do we do the cancellation or the simplification. 7 over 4, and well, we can cancel 1 power of 7. Cancel 7, power 2, and those 2 powers of 7 in the denominator will make a 49. And that times 1/4. So 49 times 4, is that 196? 196. 243 over 196. All right. And well, that's how we deal with a geometric series in which, well, we have a different starting index and we need to do some work before we can get it into the correct format. Alright, what's more about the geometric series? So we can use this series in order to find or to write a repeating decimal and turn it into a fraction. Well, like this number, 0.3 13, 13, 13, 13. When we have these decimal places, well, this means that we have infinitely many repeated decimals. This is not the same as only saying 0.13, 13, 13, 13. No, this is a finite number. This is what makes it like an infinitely many decimal point. All right. So let's use an infinite series to convert this into a decimal, or rather this decimal to a fraction rather. Okay. Another way to represent this number to avoid these dots. This is also written as 0.13 with a bar at the top. That means periodic. The number just repeats those decimals. It's a compact way to rewrite it. And well, this is how we are going to expand this number. So 0.13 equals, or rather with a bar. So this is 0.13 plus 0.0013. Though that's the first repeated 13. Plus 0.00, another couple of zeros, 13, plus 0. And etc. This just goes on forever. All right. But the thing here that in order to turn this into a fraction, we need to convert this into sigma notation, and more in particular into a geometric series that actually converges. Well, there's two elements that we need in order to write a geometric series. Number one, the first term, a, it's there, 0.13. Got it. Okay. A equals 13. That's our first term. And then from there, we need to find the value of r. How do we get the value of r? By computing by finding the common ratio. That is the ratio of the term to its previous term. So in this case, 0.13. 0.0013 over 0.13. That's going to give us 0.01, which is the 0.01 right here. Let's verify that we get the same when we find the common the ratio between the third term and the second term. So if we do 0.000013 over 0.0013, what is that going to give us? Can anyone help me with the calculator here? The same, 0.01. And of course, it's going to be the same for this. And that's our value of r. So we can write this in the form of a geometric series. N equals to 0, 0.13 times 0.01 to the n power. And well, in this case, this series is given starting at n equals 0. Well, it should work, because if we plug in n equals to 0, that's 0.13 times 0.01 to the 0. But what is 0.001 to the 0? Isn't that just 1 times 0.13? Isn't that the first term? And then plus the second term, okay, for n equals to 1, and then we will be getting this numerical expansion that we got here. All right. So let's see. Number one, let's see if the series converges first, because I mean, what if it doesn't converge? Well, then we cannot find the sum. So find the absolute value of r. That's the absolute value of 0.01, which is 0.01, which is less than 1, converges. All right. So converges. Then let's find the infinite sum. That is, this infinite sum will be the representation in in fraction. So that'll be a over 1 minus r. And a is 0.13, and 1 minus 0.01, which is 0.99. Well, we have a decimal over a decimal, so we don't really need to do any calculation, because we can just move the decimal 2 places to the right on both numbers, giving us a 13 over 99. And if you do this if you compute this number on the graphing calculator, you should get that point 13, 13, 13, 13. So go ahead and check it out, and if it's anything different, let me know. It is? All right. Well, properties of infinite series. Well, so in this case, let's consider 2 different series that we can add or subtract. All right. But the thing is that in no, I'm going to highlight. We need to make sure that both series are convergent infinite series. All right. So on the one hand, we can find the value of the infinite sum and multiply that value of the series by some constant c. Right here, that's our first property. Or we can add or subtract the values of the series. That is, the series of a sum of sequences is the same as the sum of the 2 series. That's all we're doing now. Here is a remark. So we will be asked, for example, to investigate whether it's possible to find the infinite sum. So if we split a given series into more than one term, we need to make sure that both series converge, because otherwise, if at least one of the terms, one of the series diverges, well, the whole series diverges. And you might remember this from the improper integrals example that we covered when we split the problem into 2. So we were working on the 2 integrals separately, and it turned out that the first integral that we worked on was a divergent integral. So in that case, we don't need to go and compute the other integral. So it's the same here with the series. So let's go ahead and look at one example. So sigma n equals 1 to infinity, 2 times 3 to the n minus 2 to the n divided by 5 to the n. So let's find the sum, of course, in the case in which the series converge. So number 1, let's rewrite this. Let's split this. Into 2 different series. So what we're going to do is rewrite sigma n equals 1 to infinity, 2, 3 to the n, 5 to the n, minus sigma n equals 1 to infinity of 2 to the n, 5 to the n. Well, in this case, it's possible to rewrite this into as a number r that is raised to the n power, because both numbers have the same exponent. N equals 1 to infinity, 2 times 3/5 to the n, minus sigma n equals 1 to infinity, 2 to the 2/5. And well, in this case, okay, let's just look at the values of r. Because notice, number 1, the series do not start at n equals to 0, so we would need to use the shifting on the index. However, it would be a good idea to have a look at the values of r, because if r is greater than or equal to 1, well, then why do we bother and do the shifting indexes if from there we're going to know that the infinite series will diverge? So in this case, 3/5 and 2/5 both are values less than 1, so both series will converge. So let's go ahead and do the shifting of the index. So minus 1 plus 1 minus 1 plus 1. That's going to give us the following. So sigma n equals 0 to infinity, 2 times 3/5 times 3/5 to the n minus sigma n equals 0 to infinity. That's a 2/5 times 2/5 to the n. All right. So to avoid like a lot of messy work, how about we label this? Okay, let me reduce this to 2 times 3, which is 6. Okay, yeah, I don't have to write the whole thing. Okay, 6/5, 3/5 to the n equals 0 to infinity, 2/5, 2/5 to the n. So let's label these two series as A and B. All right.